I'm sculpting the inside of the mouth. The robot's gonna be able to drink water with ice cubes in it, and that's gonna be a critical part of its cooling system. So I'm basically designing the throat right now. I don't want ice and water to come out the top of the mouth, so I gotta make this wall taller. Okay, that worked. It's got extra fluid on this funnel, but the rest of the bigger for ice cubes and stuff to fit. So all these have to be increased in size. Hey Mike. Look Mike, I finished placing all the motors in the legs. These motors govern the whole back and spine and everything. And then all the motors for the arm are basically arm and shoulder, made it into the arm and shoulder, but all the motors for the back, the abs, obliques, spine, traps, even the neck, I just ended up putting all in the thighs. So that's the thighs and the butt have all the motors for the whole torso aside from the arms, and it has all the motors for the legs. And I also built where the main PC is gonna go, which is this box right here. And I built the artificial liquid container, which is here. Let me pull it out so you can see it. It's got two chambers. The top is kind of an overflow chamber. The bottom's where the ice water will go. So as you pour ice in, the water will rise up as the ice displaces it. Once the ice melts, it'll all kind of lower down to here. Um, so I'll put that back. And then I'll show you guys the lungs. I only did one half of the robot, so there's going to be two lungs. But this is one of the lungs. There it is. He's going to have two artificial lungs. And we have two pumps here. Two different colors. These pumps will govern pumping the liquid cooling system. Actually, I'll show you guys the updated design for the liquid cooling system, so you can see what I actually did. This kind of took my existing designs and just kind of consolidated it and narrowed it down. Okay, so let's see. Here we've got the throat. That's like the throat where the mouth opening is. That's a pinch-off valve, that's a pinch-off valve. So this main tube will allow it to swallow ice water. You can see the little ice cubes. You can see the water level up here. It's going to have an inner sac that contains the ice water, but the outer sac contains distilled, demineralized water, because we don't want corrosion to build up over time, that white stuff inside pipes. The first pump pumps the water out of this icy water cooling chamber, which we could call the stomach, I guess. The first pump pumps the water out of the stomach into the artificial lungs. It will trickle down, basically like bath sponges that women use, those squishy sponges. It will trickle through the sponges and then land at the bottom, where it will pull up. These little waves represent the water line. The reason for the bath sponges is as these lungs inflate and deflate, the water trickling through the sponges will act like a swamp cooler or an evaporative cooler, and as the water evaporates, as the air passes through it, it creates a cooling effect. So it's going to have basically ice cooling system and evaporative cooling system through the artificial lungs. The artificial lungs then cool the the liquid cooling system water, and the artificial lungs actually will be doing the air transfer system to create airflow throughout the robot's body. It will basically pump air into the extremities of the body, so it will pump air into the wrists and into the ankles. And that fresh air going into the wrists and ankles will eventually rise and displace the hotter air, which will be toward the upper parts of the arms, like near the shoulder would be the hottest air, and then the coolest air would be near the wrist because heat rises. Same thing with the legs. Blowing cool air into the ankles, that cool air will rise up, displacing the hot air, which rises to the uppermost parts of the legs, so it'll be toward the upper thighs. And that air will eventually rise up through the whole torso and then out. And it's going to come out through the nose. And I can get into that later, but that's the general overview of how the air cooling system works. But we're going through the liquid cooling system only in this drawing. So it will trickle through the lungs, cooling the air and cooling the water. It will pull up at the bottom of the lungs, and then this second pump will pump the water out the bottom of the lungs, and then it'll pump it through the body, and then after it's passed through the body, it'll come back up, and it will land back into the cooling reservoir with the ice cubes in it. So that will finish the cycle for the liquid cooling. It will draw a lot of heat out of the body. These tubes are going to have segments that will be copper pipe, and all the different motors will have braided copper wire attached to them with thermal paste, and that wire will wick up heat off the motor and then be wrapped around the copper tubing, and that will allow the heat to travel off the motor through the wire and onto the copper tubing, where water will be passing through, carrying that heat out of that region and into the cooling reservoir, which has the ice cubes, which will then cool off the water, and then the water will be pumped out. The hottest water will be at the top, the coolest water will be at the bottom, so the pump pumps the coolest water out and into the lungs for even additional cooling as evaporative cooling, and then it goes back through the body and it rinse repeats over and over. Eventually, obviously, the ice will melt, so he can, if he's doing very physically strenuous stuff, he can continue to drink ice water, and he can drain out this and pee it out. This is like a little sphincter muscle, so it can pee out any ice water that's melted and warm now. So that way it can keep recharging its cold water reservoir with icy cold water. And that will be available anywhere the robot goes, because even if he's at a drive-thru, he can order ice water. So anywhere he goes, he can always access ice water. So it's a great way to get the robot cooled off if he's doing strenuous stuff. But it's possible he won't even need it if he's not doing strenuous stuff. Maybe the air cooling system will be enough, but I designed the liquid cooling system for redundancy, so we've got air and liquid cooling, so we can maximize the potential of the robot to handle all the heat being generated, especially when it's doing strenuous things. And I have some little notes here. lungs and evaporative cooling. Pump from reservoir to lungs needed to lock off lungs from exhaling into reservoir. So yeah, it's got a pinch off valve here and here, so only one will be open at a time. This will mean that the lungs can't ever accidentally push air into the cooling reservoir, causing it to blow coolant out the mouth. So yeah, we don't want it to blow coolant out the mouth by accident. What about condensation inside? That's a good question. I thought about that. My thought is that that will be an issue, and so we're going to have to probably insulate all the electronics really well and try to just minimize risk. My thought is that the condensation will not be dripping that much. It'll probably just gather on the tubing, but not drip often. And hopefully it will just kind of pool up, like in the bottoms, like in the wrists and in the bottoms of the ankles, and not touch any electronics. But we could possibly even strategically locate like cloth wrapped around the tubing in certain spots, like a little donut of cloth. So as condensate drips down the tubing, it just kind of gathers wherever you put the donuts of cloth. And my thought also is that the heat being generated by the robot would dry out the condensation with time. So like when he just drinks a bunch of ice water and really cold water is passing through, condensation might gather, but then the tremendous dry heat being given off by the motors and the batteries and everything would ultimately dry off that condensation before it has a chance to cause a lot of electronical damage. So I feel like it will just dry so fast. And if anything, like if through trial and error we find out, depending on the temperature of the water, how much condensation it produces and how much risk that is, we could stop pumping the liquid cooling system for a little while to let the condensation dry out. So we don't have to keep pumping liquid cooling through too much if the condensation gets out of control. But I just feel like the main thing is we gotta coat with conformal coating or whatever all electronics, so that whatever condensation that might occasionally drip onto some circuit board or whatever will not cause a short circuiting event, because then we got a big problem. Are you building the robotic self? Yeah, I am building it. I consider the design work to be building it, and I also consider the 3D blueprints we're doing to be building it as well. Physically building it, I do like here and there. I've been doing it off stream some too. But I keep finding as I start physically building it, I have too many questions about where things are going to go, how they'll fit. So that's why I've been actually creating the different systems. So those two little pumps you can see from the drawing are right here next to each other. They've each got an input and an output tube coming out of them. And you can see how the pinch-off system will work. Wherever you see this arrow with a line, that's going to be a muscle wire. So the muscle wire or string will be connected right here, and it will pull this way. And then we got another string that pulls the other way. So we can open and close this sliding bar, which will pinch off this silicone tube. So it's going to be a hollow silicone tube, and it will just slide this black bar and pinch off the tube. How will you deal with potential mold growth? The same way liquid cooling for computers does. They put a tiny amount of like mold killer into the distilled water. So you can buy additives. I don't know if it's like in pill form or if it's like a liquid in a little bottle, and you pour out a certain amount. Like let's say like 1 teaspoon per liter or something. So we'd put in like a teaspoon. I'm not sure if mold grows in moving water that's distilled, I feel like mold would come more so. I don't know, like, is there mold inside copper piping inside a house's walls? No. Why? Maybe there's just not enough air access. I don't know, but um, like regular water passes through piping in a house, and there's no mold inside the pipes. So where would the mold come from? Well, if there's condensation on the pipes and it drips down in land certain places, maybe that could develop mold over time. It takes a while, I think. We know mold develops a lot on drywall, but I'm not sure that mold would develop too fast on plastic materials and silicone materials. If you look inside a shower, usually mold doesn't grow inside a shower. Usually it grows like in refrigerators and stuff, but that deals with the food that it's got access to. If it's a very sanitized surface, I'm not sure that the mold has anything to feed on. I'm not sure. So I did consider mold, but like I said, the additives should take care of that risk a pretty good amount. Will I model the brain to be a CPU? I thought about it. Right now, I have no plans for inside the brain cavity of the robot. It's all just free space. I could put anything I want. If I need more batteries, I could put a bunch of batteries in here. If I want to put facial motors in there, I can put them in there. I didn't bother doing all the facial motors, so there's a strong possibility I'm going to fill it with motors and maybe some extra battery capacity area. I can show you the water, or the air, not the air, yeah, the liquid cooling piping. Let's see, which one is this? Okay, that's the air cooling. You can see it just stubs off. But the water cooling is next to it. You can see it makes a loop and then it comes back so that it can exit the body. Or no, it doesn't exit the body. It goes back into the reservoir. This red reservoir in the top of the chest, you can see it re-enters there. So it's going to pour out right through there. Right there. And so it starts out let's see. Okay, so this pump is okay. Okay, yeah, the liquid cooling starts out, as we talked about in the diagram earlier, it comes through the bottom of the lungs. The lungs are this blue box. And this pump is going to pinch off this part and open up this part. And then it's going to draw in. The pump will work just like a chimney, what's it called? A chimney... No. The thing that you put for a fireplace. Or that musical instrument that they go like this and they play the keys on the side. It's just going to squeeze and open, that's it. Just like a heart or whatever. It's like an artificial heart. So anyways, it will pinch off this one, it will open this one, it will spread open, drawing in water out the bottom of the lungs that's been cooled. And then it will pinch off the one it used to draw in, and it will open up this valve, and then it will go through the legs. It's going to follow... Okay, so it came down through here. It's going to turn. It's going to come down the inner thigh. It's going to split and come down in two paths across the calf. Then it's going to rejoin right here. And then it's going to split apart again in three directions, dividing itself across the rear of the thigh, side of the thigh, and front of the thigh. And then it's going to rejoin right here. And then it's going to come up, all the way up the side, and then it's going to turn just underneath the scapula. It's going to come down the arm. Now, it's going to be kind of warm water by this point, unfortunately, but Not if it's sitting down. So if it's running, generating a lot of heat in the legs, that will affect the arms. But I think if it's running, the arms won't be doing a whole lot anyways. But yeah, this water by this point is going to be quite heated. It's going to come down through the arm, turn, and return up the other side of the arm. So it's going near both groups of motors. And as I said, certain sections of it will be flexible, hollow silicone tubing. Other sections will be copper tubing. The copper tubing will maximize heat transfer out of the motors. So we'll have like little wires, braided copper wire, wrapped around the motors and then wrapped around the copper tubing. So the heat can transfer through those wires onto the copper tubing. And we'll use thermal paste to maximize heat transfer. Yeah, like a billow. So then, like a section from here to here will be copper tubing. And the water will pass up all the way through. All these motors will have lots of little braided copper wire coming off of them. More than one. Like one from here to here, one from here to here, one from here to here, one from here to here. Like maybe 15 to 20 of these wires will be coming off each motor. So each motor is going to look like it has a bunch of hair coming out, which will then wrap around the copper tubing. And that will draw the heat through each one of those follicles of hair, which will be braided copper wire. Solder wick wire. Hold on a second. Hold on. Okay. So, basically the more copper wire you have wrapped around each motor and the more strands of it you have wrapping to the pipe, the more efficient and quick the heat flow off of each motor onto the water cooling pipe will be. And it's the same principle as if you have a heat sink on a processor, there's a lot of fins coming off it in order to maximize surface area of air blowing across that. And that's another part I wanted to bring up. Because we're also going to have air flowing through the different parts of the body, because we're having artificial air exchange, artificial lungs that serves as an air exchange system for the robot as well. That air will be able to blow through all these little braided copper wire strands coming off of each motor, and that will cool those strands as well. So we're having not only liquid cooling but also air cooling in order to maximize cooling. So anyways, it's going to continue up. It's going to go back under the scapula. It's going to come through here. You can see it right there. It's going to come around, and then it's going to come down and into the top of the red liquid cooling reservoir where the ice water will be. And then as it cools, the cooler water will naturally gravitate to the bottom, and we'll have a pump that pumps out from the bottom, the coolest water, and pumps that down and trickles down through the lungs. The mesh sponge of the lungs, it will trickle through that, and as lungs are expanding, drawing in air, that will pass through that water, chilling the water and chilling the air through evaporative cooling. When water evaporates with air blowing across it, it cools. And that's how swamp coolers and evaporative coolers work. So it's going to have that type. I considered creating a Freon-based cooling system, but I opted out of that because I just feel creating a compressor and stuff would be too heavy, and it just, I kind of chickened out from it. I could put a Freon-based cooling system into like robot version 2 if I make another robot, which I plan to make many robots, but for now I think this is going to be fine, and we'll use ice. So yeah, that's the flow of the liquid cooling system I showed you start to finish. And then this other pump just pumps water from the cooling reservoir into the lungs. That's its only job. And we went through that in our diagram earlier when I showed you the drawings. So it's got two pumps. One goes from the cool water reservoir into the lungs, and then one goes from the lungs to the rest of the body, and then it ends back in the top of the cooled water reservoir. And so that's what these two pumps are. And look, they don't even have to be that big, because picture each one as like a piston. It's going to open and shut, and when it opens, it's going to draw just enough water, like a fistful of water. It's going to open, then it's going to pinch off, and it's going to push a fistful of water, and it can move quickly. So it's not necessary that it has tremendous size for that, but I did feel that the lungs needed to be pretty big, and you can see they're pretty substantial here. Because I feel like lungs need to be really strong and draw in a good amount of air through the nose, like a good amount, and then pinch off the nose and then push it down and through the body. And I'll show you the path of the air through the lungs. So you can see we got a bunch of pipes entering the lungs, but a couple of those are water pipes. The air pipe, I believe this might be the exit air pipe. Let me check it. Yeah, that's the air pipe. Yeah, so you can see it's just going to come up, over, and down inside the arm. It goes underneath the scapula area, so it doesn't interfere with arm movement at all. And I actually think this is probably where the arteries and veins of the arm pass too, in the armpit area. So it's pretty cool that the way the body organizes our piping is the way I'm organizing my piping. So anyways, it's going to run through the inner arm, and then it's going to stub out. Okay, that's not a perfect circle, but whatever. It's going to stub out right here near the bottom of the wrist. So a lot of cooled air is just going to be blowing into the wrist. Now what's going to happen? Well, as you send a tremendous volume of air into the wrist, that's going to displace the air above it, or else the wrist would just balloon out. But it won't balloon out because it's got a place to go. So it's going to force all this warm air up, and it's just going to keep flowing upward as the cool air displaces the hotter air, which the hot air wants to rise anyway. So the hot air will rise up through the arm, and then it will exit the arm and blow into the shoulder area. It will continue to rise through the trapezius region into the neck, and then finally it's going to exit through this tube. This is the exhaust tube for the whole body. It's all the hot air will eventually rise up to here, and we got a valve to shut that off. When the lungs draw in air, it's going to pinch that off, and air will suck through the nose, and you can see that's the nose right here. So you can see we're going in through the nose. The hot air is going to come up through this tube, and the cold air is going to go through this tube. This bottom tube has a shutoff valve, which we were just showing you right here. We'll pinch that off. So when the lungs draw in air, they open up. It'll pinch off this one, but open up this valve, and that will allow for air to be sucked in. But we don't want the exhaust hot air of the body being sucked in when the lungs breathe in. We want cold air from outside of the robot's body. Then when the lungs exhale, they're going to exhale the air into the body, not out through the nose. It's going to go in through the body with this one pinched off, but this one open. Now, when it exhales the air into the body, exiting through the wrist, where I showed you, with this valve open, all that air blowing into the wrist and into the ankle, which I didn't show you yet, is going to displace the hotter air in the body, which will all rise up and culminate in this throat region and exit through this tube and out the nose under pressure, because remember, we're pushing air out of the lungs into the extremities of the body. So all the rest of the air will flow up and out the nose. And so that's how that lung system will work. And I can show you, I showed you where the arms, the air intakes into the arms, and then the other air, it branches off. And let me show you that branching point. You can see here, the upper portion is a little bit smaller than the lower portion because we want more air to go up, over, and down into the arm than we have going into the leg. No, it's smaller because we want less air going into the arm than the legs, because the legs have a lot more motors. They'll need more air. So I was able to make the majority of the air flow this way, but you can see some will split off and go upward. And so I made this bigger than this slightly. So this section will split off and go down, 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 all the way down. It will curve this way. Notice we put plenty of slack so that when the robot's torso bends, twists, turns, etc., it's not going to have a lacking of slack on this pipe and cause the pipe to tear or something. So we need the pipe to have plenty of extra room. That's why we made wide looping angles rather than a direct path. So we got plenty of extra pipe to be able to handle the motion of the body. Comes down through the inner leg, through the inner shin, and it ends right here. And in this model it's closed off, but I could delete these faces. It's going to blow air out through here. And that will, as we said, it will be putting cold air into the ankle, which will then start displacing the air throughout the leg, which will then travel up through the body and exit through the throat. And so that is an air exchange system. All the hot air gathering in this leg and in the body and in the arm makes its way upward, and the cool air is going to here and to here, displacing all that hot air. And as I said before, everything on this side will be mirrored on this side. So yeah, that's how the air cooling works. And as I said before, the braided copper wire wrapped around each motor and then wrapped around the liquid cooling lines, which will be copper in the areas that needs to be copper, it will be silicone in the areas that need to be flexible. And we'll have a clamping the copper to the silicone so that they are merged together. So we'll be sliding the silicone over the copper pipe and then clamping it so it doesn't leak. And we'll probably need to have a little bit of a lip so that the silicone does not leak. If you have messed around with like changing your piping for your radiator system in your car, you'll notice that the rubber hosing goes over a lip on the metal, and that lip just like really seals it off where the lip is. It's like a kind of a barb in the steel, so that the rubber has to go up and over that barb, and then it's pinched off, and the barb really seals it watertight and airtight. So anyways, yeah, we'll have some type of system for that. And you can see it's pretty small tubing, but it doesn't need to be that wide in diameter. So yeah, and if you're wondering what all these black lines are, if you click on a motor and you click on a black line next to it, you can follow the black line. This black line leads to a connection point with another black line, which then leads to the actual muscle that motor controls, which is this muscle. So that motor we were looking at controls this wrist flexor muscle. And if you want to know the name of the wrist flexor muscle, you can follow it the other direction, and it will lead to the name. It's the extensor carpi radialis brevis. So we've got every single muscle of the human body labeled, and there's a ton over here. Gluteus minimus, gluteus medius, gluteus maximus. We got every single muscle of the whole body labeled. We've got a motor assigned to it, or motors assigned to it. And we've got the muscle sculpted out. We got the placard sculpted out. We got motors assigned to it. We did all of that. That was a lot of work, guys. And we made it all fit so that the motors actually fit inside the human body. And it worked. We fit everything. We've just got a few motors now up here that we got to fit in. This is the motors for the lungs and the on-off shutoff valves for the liquid cooling and air cooling systems. So we've got to still put those in. And then if you notice, and now remember, the leg's going to be totally full on this side to match this side. We've only got a little bit of room left to squeeze the rest of those motors, which we got plenty of room for those. But we also got to fit all of our batteries. So we've got all this area for batteries. We can also maybe squeeze some batteries in here. Maybe some batteries in here. No, this is going to be a highly contended for area with the arm lifting up. The whole shoulder girdle moves and it lifts up. So this area won't be able to fit much. Plus there's a lot of muscle wires going to be passing through this region for the neck muscles and the shoulder girdle muscles. So yeah, hopefully this whole area right here will be enough for the batteries. And then whatever batteries are not sufficiently provided for with that area, which it might be enough, but we're going to have him be able to strap on a battery backpack. And so the batteries on the physical robot within the body will be mainly for while he's taking off one battery backpack and plugging in the next one, he'll need like onboard batteries for that. Plus the onboard batteries will be fine for demonstration purposes, like just like a 1-minute demonstration with no battery backpack on. He can do something cool for the camera with no wires, no cords attached, no backpack on. He'll be fully able to function, but not for long. Eventually he'll need substantially more batteries in order to have a long uptime. And we can have 24/7 uptime by having him wear a battery backpack with 1 or 2 other battery backpacks always charging. So once this backpack's totally drained, he'll take it off, set it down, plug it in the wall, take off a full battery backpack, put it on his shoulders, just like a book bag, and then boom, he'll plug that in, and he'll be good to go for another like couple hours. Meanwhile, the other 2 battery backpacks will be charging, and by the time one's empty, one of the other 2 will be fully charged, and so he'll have 100% uptime in theory. That's my design, and I think as long as you have enough of those battery backpacks charging, he'll be able to keep rotating them in and have full uptime 24/7. He can be doing stuff. Plus, I don't think he'll use a lot of power when he's just like sitting down cutting out squares or whatever, but he'll use a lot more power when he's like walking around or doing some type of like dancing or something more strenuous. So yeah, I'm going to continue with what I was doing. Right now I'm creating the throat so that he can swallow ice water and it will go into his cold water reservoir. And you can see I copy pasted the air cooling system. That's why he's got this tube right here, which he doesn't need. So we've got to delete this. I'm actually glad I didn't hire somebody to do this because I was getting quotes like just to make the skeleton for like hundreds of dollars, and there's just no way I could afford that. So imagine how much it would have cost me to have somebody sculpt every muscle, label every muscle, sculpt every robot, label every... I mean, we would have been talking like... Even me paying people from third world countries to do it would have still been thousands of dollars. So it's pretty cool that I did that all myself in my spare time. Whoa, what's going on here? Yeah, I would say, even though it might not seem like I worked on the robot that much this year, this design work is really critical, and the designs are like really getting totally fleshed out, fine-tuned, not just kind of like quick sketches and concepts, but now we've got like really detailed designs getting done. So that's going to make actually building it a lot easier, and we can 3D print things in some cases right off this model. This is all to scale. It's perfectly to scale, so we'll be able to create our exoskeleton mesh as well really easily. It's all to scale on that too. We know all the motors fit. That's a big relief, because I always had this idea like, what if we don't have room for all the motors of the human body? There's so many motors, but I managed to fit all the motors. And I also didn't know, like, let's say the hamstrings, right? Let's say I wanted to put like a skateboard motor in, like those electronic skateboards for a hamstring. I was thinking like, will I have room for a motor that size? Well, it turns out I did. So a lot of questions I had, will there be room, were answered, and so that gives a lot of peace of mind, and it also tells me how strong the robot can be. And I remember I told you guys that unfortunately I could have a fully articulated human body on the robot, but it would not be that strong. It would be about the strength of like a 6-year-old girl, despite having a huge body of a man. And I was okay with that. It was just going to be a very like weak robot. It could have high speed and it could have high precision, but it's just not going to be strong. It's not going to be able to do much. Well, it turns out it can be strong. I did manage to fit enough motors to make the robot, I believe, as strong as I am. Maybe even stronger in certain muscle groups. I really put a lot of motors into the different areas that needed to be very strong, like the biceps, the thighs, the calves. I put tons of motors that I actually managed to fit them just because of the efficient way I designed placement of all the motors and everything. I really think that this robot's going to be super, super strong. So that is good news. That's a surprise. I did not think I would be able to fit. But still, I mean, something when I'm actually building the physical robot could come up where I realize, hey, these motors, though in the 3D software I placed them a lot closer than I thought I could, in real life I'm not able to replicate that for whatever reason. It just doesn't work out. Maybe they'll overheat if they're that close together or whatever. So you never know. That did kind of happen with some of the motors in the wrist. As I was placing them, I noticed that I didn't have enough room because the length of the motor neck or whatever, what's it called? The output shaft was a little bit longer in the actual motors than in my model. So I kind of had to spread them out a little more when I made the physical wrist motor area on the physical actual robot. So basically what I'm telling you guys is that I have already began placing these motors. I already have all the bones of the body done because I am using a medical skeleton, PVC medical skeleton, for the first robot, which is, that robot's name will be Abel. I mean, technically, Adam is my first robot, but I'm going to finish building Abel first, and then Abel's going to build Adam. So Adam is going to be a robot that's on hold until Abel gets done. Abel's going to be the PVC medical skeleton robot. Adam will be the fiberglass, handmade fiberglass robot. And we'll see which one we like more. I think the fiberglass might be a little stronger, maybe a little lighter weight, easier to repair. There's some advantages there. But the PVC does seem not that heavy, and it seems pretty strong as well. So we'll be able to compare the two and see which one we like the best. Really, I feel like this design work, I wanted to avoid it because I knew it would be a lot of work, and I just thought I could figure this out while building the actual robot, but it turns out it's so complex, and there's so much going on. Just winging it like that and trying to build it as I go would have been just a terrible, terrible idea. And I know you're supposed to measure twice, cut once, and I was just finding out kind of the hard way that I must do this step. It's not something I can skip. There's just too many parts that all have to fit. And carefully placing and fitting everything will mean maximizing effective use of the space allotted. And that is going to be what makes or breaks this entire project, is maximizing the space allotted. Because the whole challenge of a humanoid robot is, how can I fit all the different systems required to make it work into the form factor of a human body? And a lot of people think it cannot be done, and I proved it can be done with this design. This design actually is very valuable, but I'm giving it away for free. Just because I don't really know how I would monetize that, and I kind of promised when I started that it would be open source project. Although the AI, no, I meant the design. The robot's physical layout and design would be freely available. And I'll show you guys portions of the code, but the code is just, it's going to be just too personal, too much work just to hand it away for free. I just can't justify doing that. Alright, let me... What temperature do you think the body will be? It'll probably be like around 100, 110 degrees Fahrenheit. I'll try to keep it at or below that. And by the way, if you think the PVC bones will like get too hot and start to melt and warp, that's not going to happen, because if the robot got that hot, which I believe is like 150 degrees Fahrenheit or something like that, at that same temperature, electronics melt. So all the motors melt. The motors fail at that temperature as well. The lamination of the internal windings of the rotor and stator or whatever, the motors, will start to melt and short circuit. So the softening point of PVC is hot enough to where we're talking about our whole robot being destroyed anyways if our temperatures got that hot. So it's not going to be an issue, in other words. We must have our cooling system effective enough to not let it get that hot that the PVC melting or softening would become an issue. So that's good to know. What will the motors be powering as muscles? Every muscle of the human body has been assigned a motor. The motors act as fishing reels, reeling in fishing line. Literally, I'm using fishing line. And that fishing line will be passing through hollow tubing, working the same way as a bike brake. And that will transfer linearly the rotational force of the motor by the motor pulling on string. Now the force is linear instead of rotational. And that linear force will then work the same exact way that the linear force of a human body's actual muscles work. And it will cause actuation of the human body's skeletal structure using these artificial muscles. So that's how the locomotive or actuation system of my robot works, and that was the foundation of my entire design and build, that concept. What material for the musculature system? I'll be using hollow plastic tubing as the muscle guide hoses, which is the same tubing used for guiding the 3D printer filament for 3D printers. So I actually searched for like Bowden tubing or whatever, and then they have all different sizes. If you research into it on eBay, you can buy different diameters. So I bought really small tubing, and I've actually managed to find it. I bought a bunch of it already. It's kind of expensive though. And then for the muscles themselves, it's going to be Spectra / Dyneema braided fishing line. So pretty much you can look for like 200-pound test braided fishing line, and that will be the muscles. Although for smaller muscles like the facial muscles and muscles for the fingers and stuff, I'll be using upholstery thread, which is smaller. It doesn't need to be braided fishing line. That has 200-pound test, and that has like 20 to 30-pound test. So it's still very strong. It's 100% nylon. Okay. So this is where he's gulping down ice cubes. Remember, that's what I told you guys earlier. So it needs to be big enough to swallow whole ice cubes. It's really important. Although I did actually create muscles for the robot's jaw, and he has real teeth. So he could chew the ice cubes himself and make them smaller, which would be hilarious, having a robot like swallowing ice water and chewing the ice cubes. That's like, I don't know, it's so realistic. a robot that chews and swallows what amounts to its food. It's not really food, it's for cooling him, but humans drink ice water to cool off as well. So the fact that he'd be doing something so human, to me, would just be funny. That like the more similarities between the robot and an actual human, the more like I don't know if funny is the right word, but like the more like I don't know. Would you say funny? Like kind of cool / strange, I guess. The more peculiar and fascinating. Maybe that's the words. I don't know. So I'm just trying to get this tube lined up, and then we'll fix up the... Okay, that's off too. Oy vey. Okay. Let's get this sorted out. Yeah, the 3D modeling can tend to be pretty tedious, so I think I did show enough of it for people to know, I guess, that I actually did it. Because some people might, you never know what skeptics will do in the future. They'll say, this guy didn't build that robot. This guy's part of a huge company or team, and it's all a spoof. And they're making him like the front man, pretending like he made it, but he didn't. So just documenting that I do everything on this whole thing that I haven't had help, I think is cool, because one of the aims of the project was to motivate people that have like big dreams or goals, that it is possible to achieve like really ambitious stuff as an individual. So it's meant to be inspiring, basically. That was a goal. Inspiring people to go after their dreams. The main thing, though, is that if you believe in God, you have to get God's green light and not put your dreams as a higher priority over people, because people are more important than your dreams. So you have to have your priorities straight. Otherwise, you'll be like Ebenezer Scrooge, just treating everybody like garbage and regretting it later, and just caring about money and becoming really negative, toxic person. Okay, so I'm gonna do this. Mesh. No, select edge loop tool. Delete. And then I want to delete this edge loop as well. Yeah, I feel like what I've achieved with this 3D model is impressive enough that certain people would not think I actually did it. So that's why it's good that I have tons of footage of me actually doing this, but showing like the entire process, I don't think it's necessary, as long as I show like a sizable enough. Is that big enough? I don't know if that's big enough for ice cubes, actually, that people are convinced I did it. So like, I would say you have to show at least like 30% and show challenging stuff you did on film, so that they'll be like, okay, yeah, he definitely did it. So like, if I showed me sculpting like 400 muscles, I don't need to show me sculpting like 1,200 muscles. As long as you see I sculpted tons of muscles, then you'll know I did it all. Okay, so that should be big enough for ice cubes. Right? Maybe not. Goodness, ice cubes are so big. I mean, I really need him to be able to chug them down. Like, I don't want stuff getting stuck in his throat. I'm just picturing some big ice cube getting stuck. So he's gonna have a huge throat. You know how people like choke on a piece of food they didn't chew well enough, like a piece of steak? Well, this robot will not have that issue. He's not choking on anything. It's going right down. He's gonna have like a snake throat. Huge, crazy throat. Okay, let's just get rid of some more edge loops here. Wait, what? Select edge loop tool. I want to delete like every other edge loop right now. Use 3ds Max, cool. Fellow 3D modeler. I used to be 3D modeling in like art contests and everything. I used to be like really into it, but now I don't really do art. My wife and I actually came to the combined agreement that artists are starving artists basically, and pursuing a career as an artist is actually kind of dumb because nobody actually wants artist services that much. And so, like, people don't even really buy art. So, let the people that, like, that's all they can do, that's all they will do, they're obsessed, let them have those few jobs, like, because there's going to be enough people buying art to support some artists, but not that many. So let it go to the people that are like stuck with only that option. Someone like me that is a Renaissance man that can do a lot of things, I should probably stick to doing other stuff than art, basically. Okay, so this doesn't need to come to the bottom. So yeah, this will just basically chuck ice cubes into this bottom reservoir. And we'll just move this slightly to the side. Like so. So they're not overlapping. And this is the suction tube that pulls cold water out of this reservoir and takes it off to the rest of the body. But what I was getting at is the cool thing about being a Renaissance man and not being an artist. I actually went to school to be an artist, and then my wife and I agreed I should not pursue that as a career. But as an inventor, and now a roboticist, I have to use art for drawing out my designs and inventions. An inventor that can't draw, that's a huge problem, because it helps a lot to be able to draw out your designs, to remember them for later and to to get them fleshed out, like more detailed and stuff. There's a lot of reasons you want that ability. So I find myself still getting to be an artist, although I'm not like making art for the public so much. And I can do that a little bit. Like I'm making a sculpture for my dad's front yard and stuff. And he's planning to pay me for it. So there's some of that, but uh-oh. I accidentally selected some vertices from way back there that I was not supposed to select. Okay. Now what is this? Oh, wait. What? What is he part of? That's weird. Okay, I deleted that object. I don't even know. Wait, was that part of something else, though? No, it seems like just a standalone floating object that made its way there. That's weird. So yeah, oh, and also I'm planning to make a video game, so I'll be able to like model all my own like villains and good guys and heroes and everything. So I'll be doing a lot of drawing and designing and making all the artwork for the game and making even like a video, like the cinematics and stuff. That could be so much fun. And but I want to do that with the help of AI. So basically, I'm going to create artificial intelligence that will amount to being a whole dev team. It will be so advanced it will serve as an entire development team, and that will enable a single person to make a whole video game or video games by having AI do most of the work. Kind of like how Minecraft is. It generates the whole world automatically, like through random factors and math. I'll have my AI be able to like randomly generate a game. It will study other games and it will study my game design. It will kind of form the worlds. It will form plots. It will form all kinds of things through AI. And I'll have an AI that advanced for this robot project. So it's not like I'm creating an AI just to make a game. I'm creating an AI, and one of the benefits of the AI will be automated game development, almost automated. It's like generating a 3D environment based on a photo will be good. Like if you say, okay, create an ancient ruins level for my game. The AI will go pull up photos of ancient ruins and create 3D environments based on that. Now you might think, well, that sounds like a lot of work. Why don't you just sculpt the ancient ruins yourself? Because I already have to create the ability for the AI to generate three-dimensional environment models from flat images in order to create the vision system for the robot anyways. The robot has to be able to look at its environment and then generate 3D models of its environment in order to create pathing algorithms to path its body through and interact with that 3D model of its environment that it picked up through the webcam eyes. So converting from 2D images to 3D and then setting up interaction with its world is necessary anyways. So using that same technology to develop stuff for video games makes logical sense. Alright, so it's going to need a shutoff valve. It's also going to need another tube branching off of that. Okay. Let's start off making the shutoff valve. Oh, we just get to copy paste these shutoff valves. You actually can't copy paste in Maya without the whole program bugging out. So you have to export whatever you want to copy, then import it, and then it doesn't cause the program to start crashing over time. I learned that the hard way. My whole program was like running slow. Had like 2 FPS when I tried moving the camera around. By now it would be unusable. But then I found out that design error or bug in the program. It just has a big problem with you copy pasting is all. Okay, so we'll just stick this huge shutoff valve somewhere. I kind of don't want it that thick though. Alright, let's do this, and then we'll... Alright, let's do this. And we'll do this. So yeah, I'm super happy that I get to do art as an inventor and as a roboticist. Technically what I'm doing now is art. It's 3D modeling. And yet I'm not a professional 3D modeler making lousy money, or in an industry that's just flooded with too many people wanting to do that, and so I'm taking away jobs from people that's pretty much all they want to do with their life. I'm a guy that likes to do a lot of different things, so why like hog one of the jobs that are highly sought after and highly competitive, take that opportunity away from someone else when I have the ability to do many other things. It's kind of like a less selfish option. Okay, what in the world? This thing is needing to be so much bigger. Okay. Let's just do this. Boom. Okay. I wanted to say it polymath instead of Renaissance Man, but I'm not sure. I don't know. You guys can look it up. I just gotta keep working. I think polymath is somebody that can do a lot of things. I think that's what it means, but I'm not sure. Alright, so there's our shutoff valve. And we'll need to assign motors to that, or a motor to that. One motor can handle that shutoff valve. Okay. And then we need, oh, so that's like if the robot did a cartwheel, all the water from his cooling reservoir doesn't just come dumping out his mouth. So that has a shutoff. And then, wow, we're so close to being done. It's ridiculous. Okay, then we need one more tube. Let's snatch this one. Wait, let me first save. I got a lot of work done. I like to keep saving. Often. And I create numbered saves so that we can fall back to a previous save point. Just in case if something totally errors out the program and we cannot solve it, we don't lose everything. Imagine that, losing like several hundred hours of work. I'm not willing to risk that, so we're doing numbered saves. I also really want to finish fixing my software program that creates backups on a server externally, just in case my hard drive crash. I don't want to lose this even then, or even if my computer just started on fire. I don't want to lose all this work. And that program currently is actually not working. My internet service provider switched to SFTP, and my custom automated server backup software used FTP, and so I have to make it use SFTP now. And I started making that switch, but I did not finish it. Okay, so anyways, file, export selection, desktop. Okay. So this tube is going to be a tube specifically for distilled water filling, and it's separate from the ice water tube, which has to be big enough for ice, so it can be a lot smaller. Yet it's branching out of the ice water tube. So this is for him like chugging in distilled water with anti-mold additive. And with this tube, he will fill the non-ice water portion of the cooling reservoir. So there's going to be a bag inside here for the ice water, a bag inside this lower reservoir. So a reservoir inside the reservoir, and that bag will fill with ice water and expand, pushing up the regular or the distilled water that's normally filling this. It will push it up into this overflow reservoir, and so we kind of could sculpt the bag on the end of this, but we could just remember. And yeah, this other tube is going to go into there for the distilled water. Now, why don't we just have them drink distilled ice water? Because it's not always going to be available. So we're having regular ice water from a drive-through, from the freezer upstairs, from an ice maker or refrigerator door. You just put a cup and fill it with ice. He'll be able to get access to that anywhere he goes, anywhere that humans are. And the distilled water system is too specific. You won't be able to get frozen distilled water cubes or something. So that will be a separate system, and that won't be changed out often. That will just be sitting there for years. So this is a tube that won't be used very often. Okay, and then this tube just kind of drops down. into the top of the reservoir tank. And then he's done. So all the rest, we can delete all the rest of the faces. Look at all that. That's a lot of lines. That's a lot of work that I did all of that. Like, this is a very complex... This is very complicated. This could overwhelm somebody if they didn't do it themselves and know where everything is, what everything is. Okay, so that's the separate cooling line. So when it's filling the distilled portion, it would pinch off this bottom shutoff valve. This little skinny valve. It's a shutoff valve. It would pinch it off, and then it would fill. It would dump the distilled water down the throat, which would go into here. And since this bottom portion's pinched off, it would go into this tube here. I'm a little concerned that when it pinches off, it would pinch off where this tube enters, so I'm going to make it a little higher up. Because it's going to be like folding in. Okay, so that's good. And then we just need a shutoff valve for that tube as well. Okay. So that was it. And then now we just got to assign, let's see, 1 motor, 2 motors. We're going to need a bunch of motors. For every shutoff valve needs a motor. But that's 2 anyways. So we'll go ahead and get that going. Alright. Alright, and you'll be the shutoff valve for... main shutoff valve motor for right here. You know what? This... This could be a little bit too skinny. Let's see. That's better. Okay. So that's one motor assigned to one valve. Hey Flora, thanks for the sub. Thanks for the donation you sent a while back too. Appreciate that. I'm doing the 3D model for the robot design right now. Okay. And this motor will go for that. How's been your projects, like the gold sluice and stuff? Did you get that? How's that going? All right, let's see. Where? There we go. All those needed motors. Wow. Oh, okay. And then got it built. Nice. CNC bender. I never heard of a CNC bender. Oh, wait. No, actually I might have. I might have seen that before. Oh, they were backlogged. Wow. I guess everyone's doing projects during COVID then. That makes sense. Alright. Then we'll need 2 more motors. Let's do that next. Man, I'm so excited that you guys have no idea how long I've been doing all this modeling for these cooling lines. Well, no, it hasn't been that long, but you know how it is. It's nice to get a project done. I mean, it's not really a project. This is a project within a project. The robot itself is the project, but designing out the liquid cooling systems is a big sub-project within the robot overarching project. That's how mega projects are. They consist of hundreds of little sub-projects. And building this robot is definitely a mega project by anybody's standard. It's such a mega project that most people don't believe one person can do it, period. Although I have seen others that built their own robot, but nobody has built one like this extensive ever. But the good thing is, like, I started in 2000, maybe 14. So 6 years later, I'm still doing it, right? And making good progress. So that's proof I'm serious about it. I think the biggest thing that would stop someone from doing a project this big is that people can't stay on any project for more than like a couple years, and then they lose interest. But because this has been a dream of mine most of my life, to build a robot, the risk of losing interest is negligible, I feel. Whoa, wait. Okay, so that one's done, that one's done, that one and that one. All 4 shutoffs for the water pump systems are now motors assigned. The 2 shutoffs for the coolant reservoir intake systems are designed and assigned. The air artificial lungs intake and ventilation line motors have been assigned. I think that's it on that. Oh, we need the drainage line. Oh, the drainage line. Well, wait. Could he throw it up? I wonder. I'm picturing him doing a handstand over the toilet. I think that's extreme. I would rather have him just pee it out. Alright, so we'll need a drainage line then. Let's see. Alright, we'll create the cold ice sack 2. Alright, how about... Okay. Oh, look at that. The stomach also. You see the stomach's difference or distance from the main computer? We can definitely put quite a few batteries in that area. And actually, it's good I said that because I think we're actually going to be placing the batteries here like very shortly. We could do that right away. Uh-oh, this is going to be... Well, no, we can probably do this. Okay. It's funny, I'm creating like a P-tube. No, I'm streaming. So I guess that's basically his wiener. He has a very small wiener. It's just a tube. I mean, that's what a wiener is, right? A tube. It's gotta be centered, right? But I'm not creating like an aesthetically accurate wiener because it's not a sex spot, so I'm trying to make it like non-sexual. And then we need a shutoff valve for that. Oh, which can be near the exit point. Oh wow. Good job finding the problem, Fluoride. Okay. Alright, now let's assign a motor to that. Okay. I'm adding motors to my robot build. This is the official schematic or blueprint or whatever. Since I realized the robot was like so complicated that anytime I put anything anywhere, I had this idea that it's going to eventually have to move. But that's super inefficient to like build large amounts of the robot and then like take it apart and rebuild it over and over until everything fits. That's really dumb. It's just bad planning. So I decided I actually will take the time to make this insanely complicated schematic for the whole robot. And that's what I'm doing now. Your inspiration? Thank you. Am I using Vista? No. Windows 7. Classic theme. Let's see, how many do we put in here? 2, 4, 5, 6, 7, 8. Wait. 2, 4, 6, 8, 12. No, 10. Wait. 2, 4, 6, 8, 10, 12. 13. And how many do we need? 2, 4, 6, 8, 10, 12, 13. Hey, we finished. Okay, now we just gotta find room for 2, 4, 6, 8. Where will those 8 go? We could probably put them in this area. Alright, let's grab one. Oh wait, we had these already populated. No, that doesn't matter. Okay. High FPS. Whoa. I've been good. Just haven't streamed as much because I wasn't working on stuff I felt was worthy of streaming. Wasn't interesting enough. And I kind of just wanted to focus on streaming if what I was doing was compelling. Fluff streams are fine, I guess, just to hang out, but the social aspect of streaming, though I enjoyed it, it is a little bit of a sacrifice because I don't get as much work done. And I guess with like having a baby and stuff, I want to like clamp down on my time even more strong. Like be super efficient with it. Since I have now to take care of the baby and homeschool the baby. I'm a full-time daycare now. On top of everything else. So it's a lot. All these huge motors are all for the lungs right here. Okay, that's 6 motors, and we put one... Didn't we put one by the spine, I thought? Oh, that was the one. Okay. 6 motors. I think that's it. How many did we have to put in? 2, 4, 6, 8. We need 2 more. And then we're good. No, I think they'll fit right above here. You know, I've done pretty well on time though since I cut out TV and movies. I just do like audio stuff, audio books, sermons, testimonies, Christian stuff. Um, and then I'll work a lot of times while I listen to something. 2, 4, 6, 8. Okay, so we got all 8. Although this rib cage is kind of touching. You need to bump out a little bit. A little bit more. Okay. And now... that was it. We placed everything. Okay. So now... let's see. Nice, okay. So that motor's been placed. Oh man. I guess we're good. It's just... There's not going to be a lot of room left for the batteries, but I guess that's okay because I have to remember we're doing the battery backpack too, so that's going to help. Alright, so that motor got placed, and this motor just got placed. Okay. Um, hey Dimebag, thank you. Goes there. Three more big boys, okay. I see them. Maybe do this. Clogged arteries? The robot doesn't have arteries. He doesn't have wait. Yeah, he doesn't have fractured ribs. I don't know who's telling you this bunch of lies. But it ain't true. Okay, let's see this one. We'll go here. Two more, you say? Oh, maybe I could see that. Maybe not. Let's see. Oh, wait. Okay, yeah, it's this one and this one, okay. Put some muscle on the frail body? It's got tons of muscles. All these motors are muscles. There goes a big one in the bicep. Look at all these motors. That is a lot of motors. Look at all that. Tons and tons. Every motor is a muscle. He's loaded with muscle. I don't know if a taser would affect him or not. I guess it would depend if the taser connected to something that was a conductor. If it just stuck into the skin of the robot, the skin is silicone, it wouldn't conduct, so it wouldn't do anything to it. Whereas human skin, since it's wet and it connects to your blood, physically touching, it would conduct through the whole body. But since the robot skin is not conductive, I think a taser would not affect it. I'm like the black guy on the Terminator right now that they went to kill because he was designing the Terminator on his computer at home. I'm that guy. Someone could bust through my door at any minute from the future to kill me so I don't finish this design. I'm literally Skynet 1.0 right now. You guys are seeing it happen. Making history. Okay. He's gonna pass the Turing test. Okay. We'll delete this one. Good, good, good. Now I'll do... Okay. And... we're creating a lot of loose ends, though. I gotta tie off the loose ends. Okay. Well, the heat may come out from all the motors. Funny you ask that, because these motors actually are controls for the on-off valves and the actuation of the pumps and the artificial lungs for the cooling system, the ones I'm working on right now. So it has an elaborate air and water cooling system, which I went through at the beginning of the stream if you want to watch it, but I'll be uploading that to YouTube in like a year, since I have a huge delay backlog of videos ready to come out. But yeah, the motors will get cooled by water cooling and air cooling, so it won't overheat the robot. Also, the sound should not be loud at all, because if you've heard like an electric scooter, because they use brushless DC motors that make no sound, this should not make sound. Although I used brushed DC motors for like the fingers and the forearms and stuff, those will make some noise, but those aren't nearly as loud as a large brushed DC motor. All the larger muscles are using brushless, so they'll be pretty quiet running. Like if you look at an electric bike, they're super silent. Or if you look at a Tesla car, it makes no noise. So that's the type of technology we're using with the silent brushless DC motors for most of the motors. Now, even the motors that are for the hands that I'm using brushed to begin with to save on cost, I can replace those with brushless eventually as funds allow, or with future robots. But I try to use brushed for any weaker muscles as much as possible to save money, because the brushless are like $12 to $15 a pop, and it's going to be like several $1,000s for the motors, and so I wanted to save like $1,000 or something. I don't know. I wanted to get it cheaper here and there, but it remains to be seen how loud a brushed DC motor that's small inside the forearm of the robot will be. I know that the silicone skin should be sound deadening to some extent, but I actually have no idea. What's loud is the geared brushed DC motors of a servo, because of all the gears grinding. I'm not having any gears. If you notice, none of my motors have gears on them. And if I do need to gear down for certain motors, which I intend to do most likely, I'm going to use pulley systems to shift the gear ratio with pulleys. And pulleys with string won't make any noise. So you'll only hear the sound of the motor itself, which I believe is pretty quiet, even for a brushed motor. For the smaller ones anyways. I don't know if a large brush motor has a decent amount of scraping happening from the brushes, but these smaller motors I don't think will be that loud. But like I said, if it becomes a nuisance, I can always upgrade to brushless. And though that will be a pain, it might not be that bad, especially if the robot upgrades himself. He might be able to do all that work, like sew motors into his own arms and connect them up. Hi, Pipple. I'm back. I'm planning to keep streaming whenever I do like interesting stuff, and not do as many just social like square cutting streams and stuff, because I think that I don't really have time to socialize as much since I'm watching the baby now. 3 days a week I run a full-time daycare and homeschooling. Daddy Daycare is the title of this season of my life. Okay. So that's been assigned. Okay, I already deleted that motor. Okay. Seven more motors, and then uh-oh. 2, 4, 5. Where did I put the other? Huh. Looks like we're missing some. Maybe I messed that up. Well, we can add more. Alright, let's go ahead and... Okay. Okay. Oh, were these assigned? No. Okay, so we'll delete that. Oop. Okay. Will their reaction times be slower? I don't think so. I think the robot will be incredibly fast with super high speed reaction times. And I believe he'll be super strong. Like, as strong as me, maybe a little stronger. Also, I think the robot should be able to do like backflips, cartwheels, back bends, toe touches, front flips, all that stuff. Because he'll have like perfect... In fact, the robot might even be able to like grab like a cone, like let's say a metal cone, and do a one-handed arm stand on it and then spin his legs around so his legs are like flared out and he's spinning like a top, balancing on a cone with one arm. Stuff like that a human could not do, it'll be able to do because it'll have flawless balance algorithms. Hi, Leaspie. So he can be like a super elite gymnast. I don't think it's going to weigh that much, no. I think it'll weigh like the same as a human body. I don't know. My streaming is based on projects, so I'm going to stream when I have like cool projects. Or like, if I'm working on the robot or another good project, I'll stream it. I'm not going to stream like just to stream my life. Like before, I just streamed my life. So anything I was doing, no matter how boring, I just streamed whatever. I'm not doing that now. That's the only difference. I'll still stream anything like that's interesting that I want to put on my YouTube. I'll stream. I thought the robot was going to be pretty weak until I actually placed all the motors and found out I was able to fit enough motors to make the robot very strong. Like, not like substantially stronger than a human, but as strong as like a strong human. Like a athlete. But maybe not an Olympic level athlete, but like at least on the strong... Like on the strong side, like a very healthy human male that works out 3 days a week. Not like freakishly strong, but I think it should be at that level. That's just my guess though, based on the motors I selected and where I selected them and how I assigned them to each muscle. That's my opinion. But I have no way to know that obviously until we test it. It'll be fun to find out, but I don't want to get my hopes up too much. I still want to fall back to, if it ends up being weaker than I thought, it's still okay because the main thing is the robot needs to be able to make products and stuff. I want the robot to be able to do my chores, make products, do sports. So it doesn't have to be like insanely strong for that. But it'd still be nice if it could do cool stunts like cartwheels, flips, in-play sports and stuff at kind of a higher level. But if it just does like, if it can only do sports at a low level, like a 8-year-old child level of ability in sports, that's fine. But we're hoping for the best though. Alright, we got 4 more motors to go. What? Something's off. How could my count be that far off? It's not a big deal. We're good. I'll just have to place more motors. There's plenty of room. Although, we still have to have room. We still have to have like extra room left over for all the motor controllers and stuff. There's going to be a lot of motor controllers. If you see a lot of motors, that means a lot of motor controllers. So, and I mean a lot. We're going to have to make our motor controllers custom and as tiny as possible. Okay. Alright. Three more motors. That's all we need. That should be no problem at all. Okay. Would it be cheaper to do a maid service? Maids can't do the stuff this robot's gonna do. It's gonna be able to fix cars. That's a chore, right? For a man that is good with his hands, he'll fix cars, right? Maids won't do that. So there's a lot of things like that which the robot will be able to do. And even, like, imagine if the robot can fix cars and I just start buying cars and the robot fixes them up and cleans them and fixes any problems, orders any parts, does the repairs. And so I make like a car flipping side hustle with the robot running it. But, I mean, just manufacturing all the products I've already invented alone will be huge as far as the robot doing things most people wouldn't do. So I don't even have to come up with like side business hustles like that. I already have it. All of my inventions, which I already sell, the robot will make for me. And that's stuff that I pretty much can't even hire people to do. Or I just run into all these snags with it. There's always drawbacks. Like the Kenyans I wanted to hire, they just ended up being too lazy to even do any work. Like almost at all. I got one guy to buy a bunch of materials then before he quit. Just pure laziness, just lack of ambition, lack of motivation. Would rather just hustle and just like work once in a while. It's so weird. Like I seriously have no idea why this guy won't work. Just lazy culture. Which is kind of ironic since Kenyans produce the best long distance runners. You would think they wouldn't be lazy then if they're like so filled with endurance. Why won't they work then with that endurance? But obviously it's not going to be every single Kenyan. I'm sure there's hardworking Kenyans. I just didn't meet one. The ones I hired were the laziest people in Kenya. Just luck of the draw. And I'm not going to sit here and just keep hiring people and wasting a bunch of money buying them a bunch of stuff and then they quit and keep all the stuff I bought. It's kind of like, it was kind of like a one-time. I mean, I might try it again. I'll still be open to, if they decide to start working out, I'll still keep the money set aside. I have like $3,500 set aside to pay them to work on hand. So I'm not going to spend that. I'll leave that in a separate bank account just in case they decide to start working. But in the meantime, I'm not going to hold my breath. That money is just sitting on the table waiting for them to work. So I'm not taking away the opportunity, but I'm not holding my breath. So I just got money tied up waiting for them to work. It would kind of suck to give them a job and then take it away. Even though they sort of deserve to have the job opportunity taken away, since any employer would typically remove the opportunity if you didn't work for like... Imagine if you had a job and you just randomly never showed up for like 2 months. You didn't call, you didn't explain why you're going to be gone, nothing. You just never showed. Do you think you'd have the job when you came back? No, you would be assumed to have quit. You would have a person that said you're fired when you come back. And that's what I have every right to do, but I'm not doing it because I'm just trying to be nice and patient and stuff. But at what point does even that become... Like, if I don't hear from them for a whole year, are they still hired, or do I say you're fired? I don't know. Oh, I keep forgetting my food. Ugh. I made myself food. I know, but I'm right in the middle of something that cannot wait. I have to eat tonight, though. If you ate my dinner, I have to still make dinner then. Unless if I don't eat. One. Two. Three. Okay. So every single motor has been placed now and assigned for the cooling system and the air system, and every single muscle of the body. That's a pretty big achievement. I know, Mer. Alright, so the next thing up will be modeling and mounting the batteries in the 3D software, and the power supply general, just like the general, not actual model of the power supply like in depth, but like kind of like just a rectangular cube will do, just to show in general. Oh no, it's not that warm. You don't need to know. I didn't make enough for everyone. What did I cook? Fries and Italian sausage. It's kind of burnt because I kept recooking it. Mounting the batteries is going to be tricky because if I put that in the lower stomach region, that's a region that's going to deform a lot. When he touches his toes, like, this whole area is going to look different. Oh! No, if the batteries are all hanging from the top, loosely secured at the bottom, and he bends over, I feel like they would just bulge out. Like the stomach would just bulge out. So yeah, I think we're good with that. We'll just hang them all down like Christmas tree lights. The kind on the string that hang. He's not going to be lumpy. That's not true. It's very important he's not. His external appearance has to look real. Nothing jutting out, no sharp edges, no motor poking out the skin. It's got to look real. No, I cannot make... I don't have the option to make a female version. Females' bodies are inherently too sexual. No, because I didn't make that much. No. They're tiny bite. Quick. Oh, wow. Now I see how someone else got it. That's how you know it's not a sex bot. This is its wiener. That does not look like a sex bot wiener. Way too scientific. Yeah, I modeled this all by hand. Well, no, not entirely. The skeleton bones were from an actual scanned human skeleton, and I modified it heavily, and I made it all custom, and I improved on it and stuff. But the outer base mesh as well, I started with a stock base mesh and I modified it a lot. So it is and isn't modeled by hand. It's hard to... Every single muscle in the body is done. Every single muscle has a motor assigned to it. Some muscles have multiple motors assigned. Believe it or not, the hamstrings, I assigned like 2 or 3 of these giant scooter motors. These are to scale, so let me show you next to the hand. That is a big motor. We got like 3 of those just for the thighs. So this motor is going to be able to jump. I mean, this robot's going to actually be able to jump. Probably like dunk a basketball. No joke. But I don't know that for sure. I just know that I assign enough motors that it might be way stronger than we think. But I don't know. the fact that I was able to fit that many motors and assign that many powerful motors to the different muscle groups gave me really high hopes. I did not know I'd be able to fit this many motors in the body. That's the benefit of actually sculpting it out and seeing how it fits. You can be surprised at how much you can fit. You'll notice like there's no motors in through here or through here because as this femur bone rotates in the hip socket and rotates upwards, all of these motors in the thigh would run into anything in the way. So I can't put motors here or else it won't be able to move its legs. So it needs clearance. I tested out all the clearances. I don't want any limited range of motion because of motors being in the way. Now, a human body, like if we do this, our pectoral muscle just deforms out of the way. Our bicep will just deform and move out of the way. But that's not how it works with steel motors. So I couldn't put any motors like right here or anywhere in here because that would cause clearance issues when it tries to cross its arm over to this side of the body, which it would need to do for like swinging a baseball bat, throwing sidearm, a throw, reaching over here like if it's sitting down to reach to its side. And I want it to have good flexibility. So there was a lot of consideration that went into all the placements. We even assigned motors to the toes. Although I got a little bit lazy, you could say, and I only actuated forward backwards of the toes. So the pinky toe cannot go outward. So it won't be able to pick things up between its toes. Like spread the big toe out and this toe out and pick something up in its toes. It won't be able to do that. I could add that. I could find room for small motors like in here to do that, but even like little areas like this, you could be like, oh man, you didn't fill that. You can fit more stuff there. No. If I can fit more stuff like in these areas, I want to fit motor controllers, circuit boards for the sensory systems in the feet, like pressure sensors and stuff, potentiometers for measuring the joint angles, pulleys for the motors to gear down or gear up certain motors as needed. So I really cannot fill every single hollow of the whole thing with motors. I need room for all the other stuff. And I'm not willing to sculpt out every motor controller and place them into this model. I mean, maybe I'll regret that too. Maybe I'll think later I should have done that as well, but I want to just do that on the fly. I mean, I wanted to make the whole robot on the fly. It's not cankles. I want him to do a back bend, so his feet will be on the ground, his hands will be on the ground back here, and he'll be making a full reverse arch. Then I want him to be able to lift one leg straight in the air, then kick up off the other leg and stand in a vertical handstand. And I want to be able to make a fist with one hand and spread his legs out and spin around like a top on a fist. I want him to be able to do like cool stuff that a person couldn't do. They'd fall over. It can have better balance than a human, so I want to try to take advantage of that to have him do cool stunts. I mean, can you imagine that? A life-size robot doing that? People, oh man, people are going to go crazy if they see that. Like, it's going to be on the news. Not like a cheerleader, like a breakdancer, like that, the whirling thing they try to do, but they're not that good at it. They can do like one time, like put their fists on the ground and spin with their legs out. Basically, picture a breakdancer that's like 50 times better than everyone else. That's what I want him to be able to do, breakdancing. Breakdancing is all about balance and core strength. Nobody has much. They practice and practice and practice, and they can manage to do like one spin before they lose balance. This robot will be able to sit there and spin and spin and spin. All the breakdancing moves would be cool. If you saw the robot spinning on its head, all that stuff, that would be a breakdancing robot. That's like a great way to test the robot. If it can breakdance. Alright. I love you. I feel like a robot that can breakdance really well will be like the measure in the future of a good robot. But can it breakdance though? That's going to be the question. Alright, this is exciting. We'll actually have to go through and make a battery. All we have to do is sculpt a cylinder. That's all they are. We'll need to go get one though. It's funny because I have like this many batteries and it costs like $1,200. And I can fit like 2.5 times that many batteries into the stomach region of this, so $3,600 worth of batteries I believe I can fit into this robot. And then that's just the onboard batteries. Well, we could put like way more batteries in battery backpacks. So he's going to have good battery life, I think. The question is, do I need to put water cooling on the batteries? I'm leaning toward not. And here's why. Tesla cars have liquid cooling on them, on their batteries, but they drive using non-stop battery power at very high amps and high voltages, far more than this robot will even use to drive a whole car at high speeds on the highway. That's way more power than this robot needs. Like, a car has like what, 200 horsepower? How much horsepower does a robot have? 1 horsepower, right? 1 horse? Sounds pretty strong to me, a horse. So like, the batteries don't need to be that well cooled, I don't think. Plus, he's just going to have like bursts of energy, like breakdancing for like a minute or two. So once he does whatever stunt he's going to do, he'll stop, catch his breath, take a break. So it's like, unlike a car that's going to drive all that power for like a 8-hour straight drive no brakes. That's not how a robot's body would ever function. Nobody works that hard nonstop. So I feel like his batteries overheating will not be that much of an issue. As long as we have decent airflow, I don't think his batteries need the liquid cooling system. I'm using liquid cooling for the motors because I feel motors give off a lot of heat very quickly, but batteries I don't think give off that much heat. Especially if you use high voltage, low amps, and you don't maximize the amperage from each battery, you run a lot of them in parallel, so that the batteries aren't that challenged. If you use a big enough battery pack on an electric bike, the batteries don't even get warm, because you have way more battery amperage giving capacity than the job that needs. So like, let's say you need 50 amps, you buy a 100 amp battery. That way the battery is not even challenged. So they only start getting hot if you're really maxing them out. If you provide way more batteries than you need for the job, they don't get maxed out, they don't really generate much heat. So that's my goal, would be to try to arrange the batteries in such a way that they're not that challenged, and then they don't need the liquid cooling. The cooling system's where you'll probably have the most problems. Maybe. I think the cooling system I designed is excellent. But leaking hoses, cracked hoses, hoses that snap off, whatever, those could all be problems. Or Mike CFL brought up hose condensation, that could be an issue. No, his core temperature cannot get over like 120 degrees Fahrenheit. Like I said, if you go to the start of this video, you'll see I went into extensive detail on the design of the cooling system, and I went through it in depth. I showed everything. And it's a complex system that I'm not able to just keep showing over and over. So you can like watch the VOD or whatever, but if you see it, I'm pretty sure that you will agree that it's either overkill or just dead on. Like, it's super amazing, the design I made. And I'm not trying to brag or like boast like in a negative way. I'm just saying, like, I think the design is awesome. That's all. I mean, if you do a good job, is it wrong to say I think I did an awesome job? I don't know. I don't think so. I think I did a great job. I think it's going to work. Let me show you guys how to eat fries at home the right way. You need to have this. And you need to have this. Do that. And that. Each bite needs to have sour cream and barbecue sauce. I'm doing it wrong. Hey, dip. Put it on your spoon. It's got barbecue sauce. Now you get tip of the spoon, sour cream. Boom. I started eating these fries every day almost, so I found that ketchup got old. Nothing worked anymore. Barbecue sauce and sour cream, I don't think that's going to get old. And if you're thinking to yourself, sour cream on a French fry, ew, then consider this. It's the same as a baked potato. People put sour cream on baked potatoes. What's the difference? Barbecue sauce is a ketchup substitute. You could do ketchup as well, but I think Masterpiece barbecue sauce has a lot more to offer than ketchup. Hi, Fuski. I'm working on the robot tonight. The design work. I got a lot done. Bill Hader. I've been doing good. I run a full-time daddy daycare for my new baby. It's a girl. I wanted a son because I wanted someone to do projects with, but so when I found out it was a daughter, I was disappointed. And then everyone said, hey, you could do all the same projects with a daughter too. And I was like, really? They're like, yeah, any daughter would like to do that stuff. So I was like, shoot, I'll do that then. So I'm going to have my daughter learn computer programming, robotics, video game development, automotive repair, whitewater kayaking, mountain climbing, rock climbing, sports, everything I like. And if she wants to do stuff I don't like, she could do that on her mom's time. I'll teach her everything I know, and then if she doesn't like it, then I don't know what to tell her. We're not playing Barbies and playing with dolls and stuff on my watch. This baby's gonna help me build the robot. Well, my wife and I are open to the possibility of having more kids. A sex doll from China cannot do breakdancing, can it? This robot's gonna be able to breakdance, play sports, do chores, fix my car, manufacture products, and even make more robots. Can a sex doll from China do that? N-O. No. That spells no. This will be asexual robot, hence why its wiener is just a tube. Doesn't look very sexual. It has a working wiener. Here's the shutoff valve for the wiener. This bar will slide over and pinch it off. The working wiener is to drain out its cooling reservoir. It has a liquid cooling system. This is the cooling reservoir. It will contain liquid and ice water. It will drink ice water. And it will swallow ice cubes too. And then the cooling system is running through the robot. Think of like a computer liquid cooling system. Will have to flow through the ice water, so that will chill it. But eventually, once the ice melts and you want to have the robot drink more ice water to cool itself down more, then it will pee out the old warm water through its working wiener, which comes out the front of the reservoir, down the front of the body, and then has an actual shutoff valve. So it will pee. And it has a working mouth, and it will be able to swallow ice and stuff. Swallow cans of ice water, which will go down into this coolant reservoir. And then you can see here it'll get sucked up through this tube. You can see the ice water comes out here. It'll get sucked up through this tube, which then will lead it to a pump. The pump is here. This is the pump. The pump will then pinch off after it's done sucking. It'll open up its other valve right here, and then it will press out the cold water, which will then go into the top of the lungs, artificial lungs, right here, where it will pass through a mesh screen sponge system, and as the lungs breathe, it will cool the water even further. You can see where it enters the lungs. I'm inside the lungs right now. There's the lungs. And then that's the air inlet and outlet ports of the lungs. It's the water inlet port. And then out the bottom of the lungs should be the water outlet port, which is right here. And this will suck the water out the bottom of the lungs into another pump, which will then send the water. Oh, by the way, the lungs act as an evaporative air conditioner, so it will cool the air and it will cool the water systems. That pump will pump the water through this tube, which will go down through all the legs, providing liquid cooling to the various motors, which will be connected to these copper cooling lines using braided copper wire wrapped around the motor. So there will be like several strands of braided copper wire going from the motor to the copper line. And that will allow heat to travel down each copper strand into the copper line that water flows through, drawing heat away from the motor and into the coolant. And then the coolant will make its way all the way back up the body, through the arm, back up the arm, and then down into the top of the coolant reservoir again, where it will pour in right here. Why build it in a humanoid shape? Because it's going to look human. And it will need to be able to pass for a human in order to go shopping, drive a car, walk into a grocery store, mow the lawn, and I have people like trying to mess with it. If they think it's a human, then they're not going to like try to mess with it, right? They'll treat it. So if you have like some type of scary looking giant centipede like pushing your lawnmower, that's going to like freak out the neighbors. It's going to cause a huge thing. You can't have that driving a car. You can't have that walk down the street, walking your dog down the sidewalk. But if you have a robot that can pass for a human, looks totally real, wears a hoodie, wears gloves, whatever, it's not showing much skin, walking the dog, nobody would think twice. So to integrate into society, it has to look like a human. The human body is not inefficient. Why are you dissing the human body like that? The human body is amazingly designed. I mean, unless if you're comparing it to like a wheeled system versus legs, but legs are so much more capable than wheels because it can go up and down stairs, it can climb a rock, like a mountain, it can climb things, it can do sports, it can do breakdancing. No, I support myself financially. Well, no. I live in my parents' basement. But I pay my own car insurance. And I buy my own toothpaste. And I buy my own clothes. And I buy my own materials to do projects. Everything else my parents pay for, though. Have you seen the body parts you are making for it? I'm talking about the skeletons right here. The body parts I'm making will not pass for human. What makes you think that? Am I planning on using the creepy humanoid hands I've got? No. Yes and no. Alright, so as you guys know, I was handcrafting the robot's bones from fiberglass. And this year I realized I was going to take like another 2 or 3 years of working on it because it takes like a day or two, a full work day, or like a 6-hour session to make a single bone. And there's like 350 bones in the human body, so to save time and just jump past that step, I bought this PVC medical skeleton, and I think it's going to work just fine. But the next question is, well, what am I going to do? Throw away all the bones I already made? No. This PVC medical skeleton, I'll make the robot from that. And that's going to be robot number 2, since robot number 1 is still the robot I was working on originally. Robot number 2, using the PVC medical skeleton, is going to build or finish building robot number 1. So then I'll have 2 robots. So I'm not wasting... Okay, 206 bones. I'm not wasting the work I already did, but I'm being more efficient with my time by using the medical skeleton to create a robot that will finish building the original robot. Also, it's possible that if I can get both hands and arms working, and get the head working, that the PVC medical skeleton robot, which I named Abel, by the way. The first robot's name was Adam. The robot I'm working on now is Abel. So Adam's put on hold. I'm building Abel. Abel's going to finish building Adam. Then I'll have 2 robots, one named Adam, one named Abel. I'm still going to consider Adam my first robot because that's the one I started first. I built a lot of it for like 2 years or 3 years. Abel's going to finish it. But the cool thing is Abel can finish building his legs and the rest of his own body once his arms and head are done. Because once he has working arms, he can build the rest of himself. I keep them right next to me. Let's see. You can see that I've mounted some motors onto it already. It's not creepy! So, these robots are going to be, I would say 5% companions, 95%, no, 5% companions, 5% entertainment, and 90% utility. Utility means actually productive, useful. They're going to be working hard. They're going to be... Actually, I believe each robot will output a full, like, how do you say it? Okay, if you work full-time, you make a full-time living, right? So, you make a living wage, right? For working full-time. Well, if I have 2 robots and they both work full-time, except they work way more than that because they work 24/7, then they can work 24 hours a day instead of 8 hours a day. So they work 3 8-hour shifts. That means they'd work 3 full-time jobs. So, if I have 2 robots, that's 6 full-time jobs. That's like if I had 6 full-time jobs, which is obviously not possible. But if I have 2 robots, I have 6 full-time jobs. So pretty much, I can just eat donuts all day and just have money just pouring into my bank account while I do nothing. Here's the thing. These robots will repair themselves. If I have two robots, they can repair one another. But to some extent, where possible, they can repair themselves, literally, like fix their own stuff. In theory. Most of this is all theory. But if you guys look back 5 or 6 years to my early YouTube videos, you'll see that my theories have come a long way. I went from just talking about a concept of a robot build I want to do to now having a working, or not working, but having like a lot of stuff done. I don't know how you want to describe that. A lot of progress. How do you code them to do that? You have to give them advanced artificial intelligence with the ability to learn and research. So, let's say I told my robot to clean my car. They don't even know what a car is. They don't even know what clean means. But I think they'll know what my means. So if I say clean my car, they'll know it's something that belongs to me. They'll know it's a noun. Because when you say my something, that something's always a noun. So they'll know like certain rules about parts of speech. So they'll know car is a noun. They'll know clean is a verb based on its placement in the sentence. And so they'll look up the word clean. They'll look up the word car. They'll be able to identify what a car is and where it would likely be. And they will research how to clean a car. They'll watch videos on it. They will search the house in terms of finding the materials required to do that job. If they cannot locate the proper materials, they will purchase the materials, order them online. So that's how advanced these robots are going to be. They'll teach themselves how to do everything. They can even, maybe I'll let them even start their own businesses. And I won't even know what business they're going to start. I'll just tell them, you need to start a business and start making more money. Because I need to buy more donuts for myself. Because all I'll be doing is just eating donuts. I'll have no reason to do anything else. Because the robots do everything.